Okay, so we're going to move into probability, which is the remainder of this particular chapter. We've looked at permutations, we've looked at combinations. Now we want to move into probability, and some of what you've learned in permutations and combinations spills over into probability. The one thing I will say to you about probability is totally fractional. So the whole exercise is in fractions, and I would be inclined to use fractions more than to use decimals when you're doing probability. Now some questions towards the end will deal with decimals, nothing you can do with that, but when you're dealing with probability, it's probably easier to deal with the fraction, because the fraction is always what you require over the total. So what you're looking for over the total, that's where you're going to get your fraction. And because it's fractional, it's measured, as we said in the slides, it's measured on a scale from 0 to 1. 0 giving us absolutely no chance of anything happening. So for example, what's the probability that tomorrow is Sunday? 0, because tomorrow is Wednesday. Okay, so 1 then is the event is a definite event. So therefore, what's the probability that tomorrow is Wednesday? The answer is 1. So you have two bookends. One where there's no chance of something happening, 0. One where there is definite chance of something happening, and that's 1. Okay, what are the chances we'll be in school tomorrow? What's the probability we will be in school tomorrow? 0. What's the probability that we won't be in school tomorrow? 1. So therefore, they're the two bookends. They're the ones that are definite. In between them, you have an infinite set of fractions. So therefore, probability is on a scale from 0 to 1, and it's fractional. So anything between that is the measurement of the likelihood of an event happening. And therefore, as I tell you at the bottom of the slide, probability is always fractional. Now the notation is important. So P of X, the probability of X happening, is A over B, where A is the result, the positive result, and B is the total number of outcomes. Okay, so we use this notation here, P of E, and that's measured the successful outcomes over, as I said to you already, the total number of outcomes. So if we were to say, for example, to throw a die, and I explained this already, die is 1, dice is 2. So if you throw a die, what's the probability of getting a 4? Well, first of all, how many numbers could you get? You could get 6. How many of those 6 numbers is a 4? 1. So therefore the fraction is 1 over 6. It is that easy. Probability is that easy. So probability of 4, as you can see down here, is 1 over 6. Okay. What's the probability then that I don't get a 6? Now, those questions are related. They're the opposite to one another. If the probability of getting a 6 is 1 over 6, then the probability of not getting a 6 is 5 over 6, because the two have to make up 1. You're either going to get a 6 or you're not going to get a 6. There's nothing outside that. So if the probability of getting a 6 is 1 over 6, then the probability of not getting a 6 would be 5 over 6. Or the way I have it there in the slide, the probability of not getting an event, or an event not happening, is 1 minus the probability of the event happening. Now don't worry about the words. The maths will be easy when we start to look at them. So if I throw a die, what is the probability that I will not get a 2? Well, first of all, I would ask you to work out what's the probability of getting a 2. So, how many sides on the dice? 6. How many of those are 2s? 1. So therefore, the probability of getting a 2 is 1 over 6. The probability of not getting a 2 would be 1 minus the 1 over 6, which is 5 over 6. That's it. Okay, so just keep that in mind. So let's do a few work examples. I think these illustrate the point an awful lot better. A card is drawn from a standard pack at random. What is the probability that the card drawn is a jack? Now I did ask you to become very familiar with cards and with dice, because they're what they're going to ask you about continuously. So first of all, what's the probability that the card is drawn is a jack? So what is the probability of a jack? Okay, and you have to write that down. So ask yourself, how many cards in a pack? 52. How many of those are jacks? Well, each suite, or suit as they call them, each suit has a jack. So that means there are 4 suits, so that's 4 jacks, which is 1 over 13. And again, simplify our fractions. Okay, part 2. What's the probability of getting a spade? Now again, what's a spade? A spade is a suit, okay? And there are 4 suits. So in every suit, there are 13 cards. So you can say this whichever way you want. That 13 out of the 52 would be all the spades, which works out as 1 over 4. Or you could simply say the following. There are 4 suits, out of which 1 are spades. Don't forget what the 4 suits are: spades, diamonds, hearts, and clubs. So out of those 4 suits, 1 of those 4 is the spades. So you can say 1 out of 4, or you could say 13 over 52. Either way, you get the same answer. It doesn't make any difference. Okay, this is part 1. Part 2. Part 3. What's the probability of getting a red card? That's easy. How many different colours in a pack of cards? 2. So there are 2 different colours, only one of them happens to be red. So that's the probability of red. Number 4. What's the probability of getting a jack or a spade? Now, here's where we've got to be careful. What's the probability of getting a jack or a spade? First of all, we've got to work out the probabilities separately, okay? And then we've got to remember what the word or means. It means that you add them together. So jacks, we said already, we have it here from the previous part, it's 1 over 13. Or a spade, which is here, that's or 1 over 4. However, if this is all the jacks and this is all the spades, ask yourself a question. Does the jack of spades exist? And obviously it does, because the spades are a suit and the jack is one card in that suit. So therefore, in this 13 over 52 or 1 over 13, I've counted the jack of spades as a spade. Here, I've counted the jack of spades as a jack. So therefore, we've got to be very careful. We've counted the jack of spades twice. So we've got to remove the number of jack of spades. If the 2 are together, that's 1 out of the 52. There's the jack of spades, and that will give you, so 1 over 13 plus 1 over 4. You get 52 as your common denominator. That goes in there 4 times. So 13 into 52 goes 4. 4 ones are 4. 4 into 52 goes 13 times, and that goes in there once. So 4 and 13 is 17 minus 1 is 16 over 52. That would be 4 will go into both of those, won't it? So that would be 4 over 13. That's it. So just be very careful. A little twist on that one there, where you have a jack or a spade. So what are the jacks? You work out the probabilities individually. So the probability of a jack, let's just do it again. The probability of a jack or the probability of a spade. Now, and we'll see this later on, we'll focus on it a little bit more clearly later. If the 2 can occur together, which they can in this case, you have to take away the probability of a jack and a spade being on the same card. Now notice and, see that? Jack and spade on the same card. So we're using the intersection notation there, which I'll talk about in a few moments. So we said already the probability of a jack is 13 over 52. We had that, or 1 over 13 I should say. It's 4 over 52. The probability of a spade, well, that's 1 over 4. And then you take away the number of jack of spades if they occur twice, which is 1 over 52. So that's where I get that from. Okay, and the last one, part 5. What is the probability of us getting a spade or a red card? Now, the probability of a spade or the probability of a red card. So, probability of a spade. First of all, there are 4 suits. One of those 4 is a spade, so 1 over 4. Or means you add and then work out the probability of a red card. Well, there's only 2 colours, red and black, so it's a half. However, can I get a red spade? And the answer is no, because all spades are black. So these 2 don't occur together, so we don't have any overlap. Therefore, we will not be counting these twice. We don't have any intersection to take away. So all we've got to do there is add these together. Common denominator, obviously, is 4. So that's 1 plus 2, which will give you 3/4. So I'll talk about that later on, about this overlap with the jack and the spade, because they would be called mutually exclusive events. If they're mutually exclusive, it means they cannot happen together. If they're not mutually exclusive, the chances are they can happen together. So for example, what's the probability of getting a king and a heart, or a king or a heart? Yeah, so that would mean a king, work out the probability, a heart, work out the probability. But remember, does a king of hearts exist? Yes. So there would be overlap. He'd be counted twice. So you'd have to take away the 1 over 52 because there is 1 card in that pack that happens to be both. So you don't want to count it twice. Okay, more about that later. Now, relative frequency. The relative frequency, again, is a fraction. But what the relative frequency is it's a way of using past information to predict future events. Okay? So in other words, you take data from the past, you form the fraction that the data tells you to form, and then you use that fraction as an indication as to how things are going to progress in the future. Okay, so again, we'll take an example and have a look. So the relative frequency is a good estimate of the true probability of an event, provided that the number of trials is sufficiently large. So in other words, your past data would have to be quite good and quite substantial. Okay, and from that, you can get your probability of certain events, And then using those fractional probabilities, you can use that to predict how many times in the future a certain event might happen. So, as I told you, it's a frequency. The relative frequency is the frequency of positive outcomes. So how many times something happens over the total number of trials. And it's used, as I said already, to predict the probability of all future events. So just to take an example. Last year, there were 167 school days and Connor was late for school 22 times. Give the relative frequency of late days for the school year as a percentage to the nearest percent. Now, part 1. How many school days altogether? Total number of school days, 167. Actually, that's all we work. 167 is all you go to school for. People are always giving us, spend your life in school. You don't actually. You don't spend 167 days a year. Anyway, Connor was late 22 times out of that 167. So there's your fraction. So therefore, out of the past data, he was late 22 times out of 167. That gives me the fraction that I can now use to predict his future lateness. So let's look at part 2. Part 2 says, the deputy principal demands an improvement. The following September, Connor is late for 3 of 20 school days. Has Connor's punctuality improved? Well, first of all, we've got 20 days is what we're looking at in the future. We multiply that by the relative frequency of how late he was in the past in order to predict how many days we would expect him to be late for if he wasn't going to improve. So we take 20 and multiply that by 22 over 167, and that gives me a figure of 2.63 days. So we expect Connor to be late for 2.63 days. He's been late for 3, so therefore 2.63 is approximately 3 days. He's been late 3 days. Has his punctuality improved? No, it hasn't. It's in line with his previous lateness. So his previous lateness was 22 days out of 167. We take that fraction from past data, we multiply it by the number of future events, which is 20. They're the days that we're actually looking at. And 20 multiplied by 22 over 167 comes out as 2.63, which is approximately 3 days. But it's perfectly in line with how late he was in the past. So, has he improved? No, he certainly hasn't improved. In the Soccer World Cup, between 1986 and 2002, there were 211 penalties taken. Of these, 161 were successful. What is the relative frequency of successful penalties? Well, first of all, how many penalties were there? There were 211. Of these, 161 were successful. That's your relative frequency. So from the past data, that fraction is the fraction by which we're able to predict how many penalties we may score in the future. So part 2. If during the next World Cup 46 penalties were awarded, how many would you expect to be successful? Well, you take your relative frequency, which is based on previous history, and you multiply that by the 46 in order to figure out what fraction of the 46 would we expect to score. So again, 46 multiplied by 161 over 211, and that comes out as 35.099, which means we expect, roughly, round off to the nearest whole number, 35 of them to be successful. Okay, so that's the solution done out there for you. That's the previous question, 35 of them. Just checking to make sure it's right. Okay, so try the following yourselves. I'm going to let you pause here now and try these two questions, page 57 question 7 and page 58 question 9 and question 10. So just give them a shot. Relative frequency, build a fraction based on what the data tells you from the past, use that fraction then to predict the number of positive outcomes for the future. Okay, so now that you've looked at that particular relative frequency question, we're going to move on into set notation. And that brings us back to first year, when you were doing sets and you were doing A and B, and you were doing A or B, you were doing A and B. All that's going to come back into play now as well. The complement, A not B, B not A, all of that, the universal set. We're going to have to bring that to mind to remember exactly how that works and apply it to probability. The one thing I will say to you is this, that within the universal set, because it's probability, within the universal set, everything has to add up to 1, because 1 is the highest probability we can have. We cannot have anything higher than 1. So that gives us a nice premise to begin with. The universal set, everything within that will add to 1. So when moving into probability, where we involve two events, it's important again to remember the meaning of the two set notation symbols, the union and the intersection. Now, this is what I want to highlight. The union is also another way to say the word or, which is another way to tell you to add. So now we've got three things which represent, three different symbols representing the same thing. The union representing the word in English or, and the word or in mathematics represents the function addition. The intersection is the word and. Now the way I remember it is the intersection. There's an N in the word intersection, there's an N in the word and, so therefore the intersection means the word and, which in mathematics stands for multiplication. Okay, so just keep those two symbols in mind. The union means or, which uses addition, and the intersection means the word and, which uses multiplication. So in some two event experiments, we talked about this already, the outcomes cannot occur simultaneously, and then there are other events where the event can occur simultaneously. So for example, it's not possible to select a card that is both a diamond and coloured black, for the very simple reason that diamonds are red. So you'll never ever get in a pack of cards a black diamond. Okay, they're just not going to happen. So that's what we say, the two events are mutually exclusive. They cannot happen at the same time. Therefore, as I told you here in the notation, there will be no overlap between D and B. There'll be no overlap between diamonds and black cards. That's the symbol for, don't forget, the null set. Okay, so that simply tells me that there is no overlap between diamonds and blacks. In other words, they can't happen on the same card. It is possible, however, that the one card can have two events. We had this earlier on in relation to the spades and the jack. So for example, in this case here, if I was to choose two cards, what's the probability, if I was to choose, a card, what's the probability that the card would be a king and a diamond? Well, the answer is quite possible. There's one of the king of diamonds in every pack of cards, so they can occur at the same time. So kings and diamonds are not mutually exclusive, because within the suit diamonds there is a king. So therefore, if you were to ask a question, what's the probability when I select a card it's a king or a diamond? Remember, you work out the probability for a king, you work out the probability for diamonds. The word or means that you add them together, but then you've got to remember, if I have counted him as a king, but also counted him as a diamond, then I have to subtract 1 over 52 because I've counted him twice, because the king of diamonds is only one card within that particular pack. In experiments with two events, which I'm going to call E1 and E2, we work out the individual probabilities first. And then, if they are mutually exclusive, then we just leave them, we add them. If they are not mutually exclusive and they can happen together, we add them and we subtract whatever the intersection between those two events would be. And that's all I'm saying here. There are three possible outcomes for two events. First of all, the probability of event 1 or the probability of event 2 where they are mutually exclusive. In other words, they can't happen together. If that's the case, you work out the probability of V1, you work out the probability of V2, and you simply add them together. Because there's no overlap, there's nothing to take away. If they are not mutually exclusive, if they can happen together, then you work out the probability of event 1, you work out the probability of event 2, you add them together, but then you take away how many times those two events overlap. That's extremely important. So when you're using the word or, if they ask you about event 1 or event 2, you have to decide, are these mutually exclusive? Are they not mutually exclusive? And then decide which one of those two particular formulas you're going to use. Okay? What about the word and? Probability of event 1 and the probability of event 2? That's easy. When you have the word and, you just simply work out the probabilities and you multiply them together. There's no conditions on that. So the only condition exists when you're using the word or, event 1 or event 2. You have to ask yourself, are they mutually exclusive? Are they non-mutually exclusive? And depending on what your answer is there, you either add them or you add them and subtract the overlap. So if they are mutually exclusive, if they can't happen together, add them together. That's it. If they can happen together, add them together and take away the number of times that those two events overlap. Okay, so here's a question. What is the probability of selecting a card from pack that is a jack or a heart card? Now, since it's possible to have both on the same card, they're not mutually exclusive. So the first thing I notice is we're asking or, a jack or a heart. So we work out the individual probabilities of both. The jack, as we already know, is there's one in each suit, and there's 4 suits. That's 4 over 52, yeah, and then which is 1 over 13, because there's one jack in every suit. So there's 13 cards in a suit. One of those is a jack. I don't mind what way you work it out, as long as you understand how it's worked out. And a heart, well, heart is 1 suit out of 4, so it would be 1 over 4. Now, you've got to ask yourself a question: do I just add them together, or are these guys non-mutually exclusive? Can a jack and a heart happen on the same card? In other words, can we have a jack of hearts? And the answer is yes, we can. So therefore, these are not mutually exclusive. So we work out their individual probabilities, and then we take away the number of times that the jack and the heart overlap, which is 1 over 52, because 1 out of 52 cards is the jack of hearts, and we end up with the following. Work out the probability of jacks, work out the probability of hearts, and take away the number of times that they overlap, which gives me, as we said already, 4 over 52, yeah, for the jacks. There's 4 jacks in a pack of cards. Then there are 13 over 52 hearts, because there's 1 suite, that's a quarter. And then you take away the intersection. 1 out of the 52 will be the jack of hearts. So when you do that on your calculator, you end up with 16 over 52, which is 4 over 13. Try as best you can maybe to keep the denominators close to each other in value, because it just makes the addition and subtraction easier. I could have said here 1 over 13. I could have said here 1 over 4, but they're different denominators. So instead, there are 4 jacks and 52 cards. There are 13 hearts and 52 cards, and there is 1 jack of hearts and 52 cards. So I kept the denominator the same in order to allow me to just add the numerators. 4 and 13 is 17, minus 1 is 16, then do the simplification at the end. Okay, so this is just a way of showing exactly what we're dealing with there. If 2 events are mutually exclusive, then the sum of their probabilities will always be less than 1. For the very simple reason that you can't have a probability greater than 1, ever. There's no such thing as a probability of greater than 1. Remember the 2 bookends? 0, definitely never happen. 1, definitely will happen. There's nothing outside those. Everything happens in between those bookends. So if 2 events are mutually exclusive, they can't happen. So for example, black cards, diamonds. No such thing as a black diamond. Here, black cards, and then we've got kings. So can you have a black king? Yes, you can, because you have the king of spades, you have the king of clubs. Okay, so that's just a way to show you set notation wise. So let's take a look at this. X, Y, and Z are 3 events where Px is 0.7, Py is 0.1, and Pz is 0.6, P standing for the probability. Explain why it is not possible for X and Z to be mutually exclusive. Now let's take the probability of X. The probability of X is equal to 0.7. The probability of Z is equal to 0.6. Now, if I add those together, what do I get? Well, I get 1.3. Can you have a probability of 1.3? Never. So therefore, it is not possible for X and Z to be mutually exclusive. If they were mutually exclusive, then the probability would be 1 or less. Okay, that's what you've got to remember. So you can't have probabilities of over 1. Okay. In a class, there are 14 boys and 16 girls. 3 of the boys and 2 of the girls wear glasses. A student is chosen at random from this class. Find the probability that the student will be 1 a girl, 2 a boy, 3 a person who wears glasses, 4 a boy who wears glasses. This is a very straightforward question. First of all, in a class there are 14 boys and 16 girls. That's 30 students. Just keep that in mind, because that's everybody. So we put them together as a collective group. Find the probability that this student will be a girl. So out of the 30, how many are girls? Well, what are we told? There are 16 girls. So 16 out of 30, which is 8 over 15. And always break down your figures, yeah? Part 2, what's the probability of the student being a boy? Now, you can do this in one of 2 ways. You can go up here and say 14 over 30, or you could say that if there's 16 over 30 represents the probability of a girl, then 30 over 30 minus 16 over 30 gives me 14 over 30. In other words, the rest, the other fraction makes up 1, would obviously be the boys. But here, 14 boys out of 30 students, so it's 14 over 30, which gives me 7 over 15. And even if you add those 2 together, you get the 15 over the 15, which represents the whole class. So it's a nice way to check as well. Number 3, a person, what's the probability that this person that this student will be a person who wears glasses. So the probability of somebody wearing glasses, P of G, and I suppose I should be writing down the terminology as well. A probability of a person wearing glasses. So out of the 30, how many wear glasses? Well, it tells you here 3 of the boys and 2 of the girls wear glasses. Collectively 5. So it's a sixth. And number 4, what's the probability of a boy who wears glasses? So boy with glasses. Now in this case, out of the 30, how many boys wear glasses? Well, it tells you up here. 3 of the boys wear glasses. So 3 out of 30, which is 1 over 10. And always make sure you simplify. Now that's a very straightforward question. Let's move on. X, Y, and Z are 3 events. X and Y are mutually exclusive. Y and Z are mutually exclusive. The probability of X is 3/5. The probability of Y is a 1/10. And the probability of Y union Z is 17 over 20. Find the probability of X union Y. Now don't forget what we mean by X union Y. So number 1, the probability of X union Y. Union means the word or, which in mathematics means we add. So that means we're going to work out P of X and we're going to work out P of Y. But we've got to ask ourselves a question. Are X and Y mutually exclusive, or are they not mutually exclusive? Because the or is where we've got to just be a little bit cagey. And we're told up here, X and Y are mutually exclusive. Good. So there's nothing, no overlap, nothing to subtract. So we just work them out separately. P of X is 3 over 5. We have that already from here. P of Y is 1 over 10. So when you add the 2 together, you'll get 6 plus 1, which is 7 over 10. And just in case you're wondering, common denominator is 10. 5 into 10 goes twice, times 3 is 6. That's where I get the 6 from there. Okay. Part 2. Find the probability of Z. Now, notice up here, we know what the probability of Y union Z is, and we know the probability of Y. So therefore, if I want to work out the probability of Z, the probability of Z would be equal to the probability of Y union Z minus the probability of Y. Now, just check, are Y and Z mutually exclusive? Yes, they are, thankfully. So that means we can work this exactly as it is. The probability of Y union Z is 17 over 20, minus the probability of Y is 1 over 10. So therefore, that's 17 minus 2, which is 15 over 20, which is 3/4. Okay, so they do become quite easy after a while. And then it says part 3, find the probability of X and the probability of Z, or add, I should say. So the probability of X or the probability of Z. Okay, just be careful with your terminology. So P of X, what are we told already? It's 3 over 5. Probability of Z, we've already found, is 3 over 4. So when I go to the common denominator of 20, 5 into 20 goes 4 times, that's 12. 4 and 20 goes 5 times, that's 15. What does that give me? Oh, do you notice anything? This here, they are not mutually exclusive because I'm after getting a value that's greater than 1. So because that's greater than 1, they are not mutually exclusive. So there's overlap somewhere. Part 4, Joanna says it is impossible for X and Z to be mutually exclusive. Is she right? Absolutely. Because of the fact that the probability ends up greater than 1, which is impossible, they are not mutually exclusive. So she's spot on. Good on, Joanna. Okay. The Venn diagram below shows the number of elements in each subset. So for example, the number of elements, remember that symbol? That symbol there just means the number of elements. When I'm doing this with the first years, I always tell them, when you see that symbol, you count. Okay, just you count the number of elements in a given area. So for example, the number of elements in A intersection B is 3. There it is. The intersection's in the middle. Part A. An element is chosen at random from the set S as shown. Write down the probability that the element will be in the set. Okay, now we've got to be careful because this is the universal set here. See that? So in other words, we've got the 8 in here too. So what's the total number? 8 and 2 is 10, 3 and 7 is 10. The total number, so the total number of the universal set is 20. So just keep that in mind. 10 and 10. So we've got 20 altogether. So everything will be out of 20. Write down the probability that the element will be in set A. So what's the probability of A? The probability of A is 10 over 20, which is half. And he knows I deal with fractions all the time. Okay, that's part 1. Part 2. What's the probability of b? Okay, probability of b is 5 over 20, which is a quarter. Part 3. A intersection b. So the probability of A intersection B, there's the intersection B, is 3 over 20. So far so good. Part 4, what's the probability of A union B? Well, out of 20, what's A union B? 7 and 3 is 10 and 2 is 12. Because don't forget, union means you add them. Intersection means you go between them like that where there's overlap. Okay, part 5. What's the probability of A less B? Remember that? Or A less B. So A less B. So you take away that. So it's only 7. There's A. Ignore B, which means it's 7 over 20. Part 6. Probability of A not B, or, that's what union means, the probability of B not A. Okay, so first of all, the probability of A not B. So A not B, we've worked it out before over here, is 7 over 20. Or means you add B not A, so that's 2 over 20. That gives me 9 over 20. Okay, part 7. What's the probability of anything? What's the dash? The dash is the complement. Everything outside of A. So in that case, again, out of 20, how many elements are outside of A? How many elements outside of here? Well, there's these two. 2 and 8, which is 10 over 20, which is a half. Okay, and part 8. I hope you can read my writing. The probability of A union B outside, complement, not, as we will say, it's probably of A union B not, so that means you're outside A union B. So A union B is all of this here. There's A union B, so I want everything outside that, which is 8 over 20, which is 2 over 10, which is 1 over 5. Very straightforward. Okay, set notation, nice to bring it back again. Okay, part B. Verify the following. Okay, so verify means it has to happen. You can't get anything outside of what they're telling you here. So these have to make sense. So the probability of A not B should be equal to the probability of A minus the probability of A intersection B. Okay, work it out. Write down what it is underneath. We already know the probability of A not B is 7 over 20. We know the probability of A, just go back here, up here and use these, is a half. Minus the probability of A intersection B, which is here, which is 3 over 20. What's that going to give me? Well, 7 over 20 should be equal to, isn't that 10 over 20? Minus 3 over 20, nobody can argue with that. So I verified it. And the second one, down here, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. See that? Probability of A, probability of B minus their intersection. So in other words, A and B are not mutually exclusive. They have overlap. Okay. So just nice to just bring these things to mind whenever you see them in questions. What's the probability of A? A half. What's the probability of B? Go back up here because all your answers are up here. Quarter. And what's the probability of A intersection B? A intersection B is 3 over 20. Okay, so a half is 10 over 20. That's 10 over 20. A quarter is 5 over 20 minus 3 over 20. Excuse my writing. That gives me 10 and 5 is 15. Mind you, that's 12 over 20. Yeah. Now, what's that? That's 6 over 10. Isn't it 6 over 10? 12 over 20. Well, just check. What is the probability of A union B? Go back up here. The probability of A union B is 12 over 20, which is exactly the same thing as I got down there. So they're quite easy to do once you understand the universal set and you understand that for probability within the universal set, everything adds up to 1. Okay, the probability of B is 0.8. the probability of A intersection B is 0.3, and the probability of A not or outside of A is 0.6. The first thing I think I would do here is I would want to see this on a Venn diagram. So the first thing I'm going to do is I'm going to draw a Venn diagram just to see what the sample space looks like. Okay, we're told that we've got A and B. We're told there's overlap. There's A and there's B. Now, always begin, you remember this from first year, you always begin in the intersection. So that's 0.3. Okay, now what about B? B is 0.8. So all of B is 0.8, which means 0.3 is already in there. So that's 0.5. We're told everything outside A is 0.6. So everything outside that circle is 0.6. So therefore 0.5 and 0.1 brings me up to 0.6. See that? Because A complements everything outside of A is 0.6. So if that's 0.5, 0.1 must be outside A and B in the universal set, not part of A and B. And then what are we told? Find P of A. What did I tell you about the universal set when it comes to probability? Everything adds up to 1. It's the highest number we have in probability. 0.3 and 0.5 is 0.8, plus 0.1 is 0.9. 0.1 in there. That brings me up totally to the total of 1. Okay, so find P of A. We've done that. And part 2. So P of A, let me just write that down. So P of A is equal to 0.1. Now remember I said to you, work in fractions? Yeah, so you could say 1 over 10. But look, because this question is dealing with decimals, just deal with decimals, it's fine. If the question deals with decimals, you deal with decimals. If the question doesn't deal with decimals, you deal with fractions. So part 2, find P of A union B. Well, A union B, what is it? A union B is everything inside this here. See that? Everything in there. So the probability of A union B is 0.1, 0.4, 0.9 over 1, which is 9 over 10. Okay, and they want you to verify that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. So again, you notice A and B are not mutually exclusive, and the diagram shows you that. A and B have overlap, so they're not mutually exclusive. They can happen together. So that's the rule for this thing here. So what's the probability of A union B? We already said it's 9 over 10. What's the probability of A? The probability of A is 0.1 and 0.3. That's 0.4, which is 4 over 10. What's the probability of B? 0.3 and 0.5 is 0.8, which is 8 over 10. And that's minus the intersection, 3 over 10. Can't argue with that. 9 over 10 is equal to 4 and 8 is 12 over 10. Minus 3 over 10. So 9 over 10 equals 9 over 10, which is true. Okay. Last one, because it's important that you see how these things are done before I let you off to do some yourselves. There are 20 tickets in a bag numbered 1 to 20. Good. So therefore we're dealing with 20 tickets. So that's going to be everything you choose from. The numbers 1 to 10 are red, so that's 10 red. The numbers 11 to 16 are blue. Now be careful, 11, 12, 13, 14, 15 and 16. So that's 6. So 6 blue. And 17 to 20 are green. 17, 18, 19 and 20. That's 4 green. Okay, so we've got 20 tickets broken up as follows. 1 to 10 are red. 11 to 16 are blue. And 17 to 20 are green. Okay, part A. 1. Find the probability of getting a green ticket. So find P of G. Okay, out of 20, how many are green? We'll go up there, 4. Simplify, 1 over 5. Part 2. Find the probability of a ticket that is not blue. Now, we had this before. A non-event is 1 minus the event. So what I'm going to do here is I'm going to say the probability of not being blue is 1 minus the probability of being blue. Just easier to work out. Which is 1 minus, how many of the 20 tickets are blue? 6 of them. Which becomes 14 over 20, which is 7 over 10. Okay, part 3. A ticket that is red or even numbered. Now, a ticket that is red or even numbered. Pause. The word or. Are they mutually exclusive? Are they non-mutually exclusive? Can red and even happen together? Are there even red tickets? Go up here. Yeah, between 1 and 10 is red. So that means 2, 4, 6 and 8 are even reds. So this is not mutually exclusive. So therefore, what we've got to do, and I mean you could count them, but these are small enough examples. So you could actually say the probability that it's red or even numbered is the probability of red plus the probability of even numbered minus, don't forget, because it's minus, let me just change that there, eraser. Oops, sorry, eraser. Oh, it's not working for me. No, okay, sorry. So P of R minus P of E minus the probability of red intersection E. Okay, so let's work this out. What's the probability of red? 10 over 20. What's the probability of getting an even number? Well, it's half as well. It's 10 over 20. 10 of the 20 numbers are even. Half of them are even, half of them are odd. Minus the probability of getting a red even number. Well, reds are between 1 and 10. So 2, 4, 6, 8. So 4 of them are going to be even and red, which means 10 and 10 is 20, minus 4 is 16 over 20, which is, you can divide across by 4, 4 over 5. Okay, part 4. A ticket that is green or odd numbered. So probability of green or the probability of odd number. Now, again, ask yourself a question. Can green and odd occur together? Are they mutually exclusive? Are they non-mutually exclusive? Can we have odd greens? So go up here to green. Green goes from 17 to 20. 2 of those are odd, so there is overlap. So therefore you're going to take away from that the probability of green and odd. See? Now I know you can work this out in your fingers if you really want to, but at the same time, let's just show you the rule in action. So the probability of green is what? 4 over 20. We get that from here. It's 4 green. Plus the probability of odd, well, that's half the tickets because they're either even or odd. So that's 10 over 20. And then you take away from that the probability of green and odd. So go up here. Green goes from 17 to 20. So 17 and 19, they're both odd. So 2 out of the 20 are what we would say odd greens. Okay. Green party, odd? No, no. Odd greens. No, we won't go there. I know we're still in election fever, we won't go there. 4 and 10, 14. Minus 2, 12 over 20. That gives me again 3 over 5. So you can divide above and below by 4. Okay, part 5. I'm running out of space here. A ticket that is red and even numbered. Now, do you notice the difference here? Red and. For and, it's the intersection. The intersection means multiplication, no conditions. You just work out the probability of red and you work out the probability of even and you just multiply them. There's nothing to worry about. For the and rule, it's simple. You just multiply the two probabilities. So probability of red is 10 over 20 multiplied by the probability of even, which is again 10 over 20, which gives me, because half of them are even, gives me 100 over 400. Now think, that's going to be 1 over 4. Okay, let's think about that. A ticket that is red and even numbered. So just go up here. How many even reds do we have? 2, 4, 6, 8 and 10. Yeah, that's 5 out of the 20. 5 out of the 20 is 1 over 4. So the rule works. And I'm just doing this to show you the rules. Okay, so finally then, part B. Is it true to say that getting a multiple of 7 and getting a green ticket are mutually exclusive events? So in other words, getting a multiple of 7. Where's 7? Where's the green tickets? The green tickets are here. So are there any multiples of 7 in there? Well, what are the multiples of 7? 7, 14, 21. There are no multiples of 7 in there. So is it true to say that getting a multiple of 7 and getting a green ticket are mutually exclusive? Yes, they can't happen together. The multiples of 7 are 14 and 21. Green tickets only go from 17 to 20, so you can't have a green ticket with a multiple of 7, so therefore they are mutually exclusive. So is it true to say? Yes. Why? Because you can't get a green multiple of 7. Okay, so nice questions to work through. Oh, sorry, one more. I thought I was finished. One more. And again, a set notation question, which is nice. Then I think the questions after this are for you to do. Yeah, they are. Okay, so let's go on and do this last one. Again, notice all of these should add up to what? 1. It's a probability question. All of these have to add to 1. You'll notice this k in here, very simple to work out. You just add all of these together and then you take it away from 1 to get k. So let's take A part 1. Now I'm going to use a calculator for this. So what have we got? We have 0.2 plus 0.1 plus 0.3 plus 0.07 plus 0.05 plus 0.15 plus on the outside 0.05, and that gets me to 23 over 25. Now decimal form, use your decimal form because of the fact that the question's in decimal form. So first of all, it's going to be 1 minus what you have. When you add up the decimals that are there, they come to 0.92, which means that k is going to be equal to 0.08. Okay, so now that you have k, you've got everything you need. So 0.08, 0.08, put that in there. So let's go, part 2. What's the probability of x or z? Now, probability of x union z. So just go and have a look. What's x union z? X there, union z. So it's everything in those two circles. Now you could use the rule if you want, or you could just use the diagram. It's everything inside those two circles. So that becomes 0.2 plus 0.1 plus 0.07 plus 0.08 plus 0.15 plus 0.05, and that comes out as 13 over 20 or 0.65. You can give the 30 over 20 back if you want to, but 0.65 is in line with the decimals in the question. Number 3, P of x intersection z. So where is x intersection z? Isn't it there? So it's 0.07 and 0.08, which is 0.15. It's as easy as that. Number 4, probability of y less x union z. Now we've got to try and figure out where that actual area is. Y take away x union z. So take y and take everything that's in x and z out. What does that leave you with? Just 0.3. 0.3. And part 5 of that, P of z complement. The probability of everything outside z. So everything outside z is going to be what? Everything outside z. So that includes everything outside z. So we have 0.2, 0.1, 0.3 and 0.05. Did I include 0.05 in the rest of those P and Z? I did, yeah. So y, yeah, fine. So P of z complement. So therefore z complement is everything outside of z. So that's 0.2 and 0.1, which is 0.3, and 0.3, which is 0.6, and 0.05, which is 0.65. Okay, so don't forget that little 0.05 out there. You'd nearly overlook it because you're working within the circles. And then the second part, B, says that they want you to verify the following. P of y union z is equal to py plus pz minus py intersection z. Again, notice there is overlap. They're not mutually exclusive. So therefore, P union z. What's P union z? We'll go in here. Probably of y union z, I should say. Y union z. Well, y union z, let's work it out, is 0.1 plus 0.3, which is 0.4. So these two, and then 0.08, so plus 0.08, plus 0.05, plus 0.07, plus 0.15. So that comes out to be 0.75, 0.75. Okay, let's see if the rest of this works. Probability of y, that's 0.4 plus 0.08 plus 0.05. That comes out as 53 over 100, that's 0.53. Probability of z, what does that come out as? 0.07 plus 0.08 plus 0.05 plus 0.15, which comes out as 0.35 minus P of y intersection z, which is 0.08 plus 0.05, which is 0.13. Now if I've done my maths right, 0.75 should be 0.53 plus 0.35 minus 0.13, and lucky enough, 0.75 it is. Okay. The last one, the probability of y complement, let's do it here. Probability of y complement, that's everything outside of y, is 1 minus the probability of y. Now, it makes sense, yeah? So we want to verify this. So what's everything outside y? Everything outside of y is all of these, okay? So everything outside of y. So it's your 0.2 plus your 0.07 plus your 0.15 plus your 0.05, which is outside down there, don't forget that. And that gives you 0.47. 0.47 equals 1 minus the probability of y. So that's going to be what? 0.1 plus 0.3 plus 0.08 plus 0.05, which works out as a half, which is 0.5. Oh, is that right? 0.5. Try that again. So y complement is, maybe I added up that wrong, 0.2 plus 0.07 plus 0.15 plus 0.05. That's 47. And 1 minus p of y, 0.1 plus 0.3 plus 0.08. Ah, yeah, I know what I did there. 0.08 plus 0.15. Not 0.05. And that comes out as, yeah, 53.53. Sorry, 0.53. Be careful with your calculators. Make sure you hit the right buttons when you're using a calculator, because sometimes get you into trouble. So can't argue with that. That's also true. Okay, look, I've spoken for long enough. There's some questions for you to do. Probability with set notation, quite easy. Are they mutually exclusive? Are they non-mutually exclusive? When do I bring it into play? When you're using the word or you're using the notation union. Okay, if you're using or union, ask yourself before you do any mathematics, can these two events happen together? And if they can happen together, they are not mutually exclusive. So you have to work out the individual probabilities at them and subtract then the fraction that represents the probability of number of times that those two events happen together. Look, I'm going to leave you with those questions there. Again, if there's any questions with these, any difficulties with these, do come back to me.